Hi, I'm Scott Lewitt, President of Structural Composites, and I'm here with Manufacturing Pathways to give you the basics on composites. This is Lamination 101. Thank you for attending. So we start with the beginning. What are composites? Composites are a result of two or more materials that come together that give us properties that are better than either one alone. So we combine these materials to get the best properties of each. In the case of composites, in the case of fiber reinforced composites, we'll use fibers such as fiberglass, Kevlar, which is called aramid fiber, carbon laminates, polyester fibers, and we combine those with resins that hold those fibers together to form the composite structures you see here like boats. So the pictures of the boats here are fiberglass boats, and these are built with fiberglass fibers and polyester resin. The two different types of resins that we need to talk about. Resins are either thermosets or thermoplastics. The boats you see here are thermosets. Thermoset resins cure by a reaction. So once we mix the chemicals together, they form a chemical reaction. It causes heat. It transforms the material from a liquid to a solid. And while it's in that liquid state, we're saturating all the fibers, allowing it to cure. This chemical curing process is called cross-linking. The other kind of plastics are thermoplastics. Thermoplastics are distinguished from thermosets because they can be reformed. When they get hot, they get soft and they can melt. And when they get hard, when they get cooled, they get hard again. So the type of plastics you see in a milk bottle or a water bottle, those are thermoplastics. And the type of plastics you see in a composite boat are normally thermosets. So the history of composites is very interesting. In modern composites, we date all the way back to the 20s, but we can really go back further because there's some good examples of nature's composites. A tree, for example, is a composite. We have the wood fibers and the sap, the lignin, holding the wood fibers together. And trees are a great example of combining fibers and resins. And you see how tough trees are and fatigue resistant. So modern composites started in the 1920s with the invention of phenolic resins. And if you look back into the old telephones you saw in the 40s, 50s, and 60s, these look like plastic phones. They were made by pressing phenolic resin with different fibers in a heated process. It made a very nice, tough material, particularly good for smaller items. And this started us down the path of composites. And back then there weren't many fiber choices, so they were using cottons and other kinds of fibers that were available. After World War I and in World War II, the need for lightweight aircraft really drove a lot of technology. And lighter weight aircraft drove the aerospace industry into composites, in particular the Air Force. And this technology trickled down into our industry, in the boating industry. And after the war, these industries that had learned how to do composites transitioned to boat building. And you'll see a lot of examples of early boats in the 40s and 50s. By the 1960s, composites were really starting to show up in a variety of uses, and in particular with boats. And in the early 60s, the first fiberglass production boats were showing up to boat shows like the Miami Boat Show. And they were different. Everybody used wood before that. So these boats were quite controversial. And in fact, the Engine Manufacturers Association tried to ban this new material called fiberglass because the wood guys were really threatened by it. We fast forward to the late 60s and early 70s, and the use of wood in boats really transitioned, and composites became the dominant material of choice in the 70s and 80s. And so now we built composite boats with fiberglass. They still used a lot of wood on the interior, on the framing, and on the structures. And so towards the late 80s, we started refining those materials and even getting the weight out of the composites, making composites lighter and lighter. And in the 90s, there was a big drive with getting more and more weight out of boats and removing wood. That was the big driver because the material that didn't last in your boat was the wood. So in the 90s, products like we invented called Prisma preforms came in, and these took all the wood out of the boats and led to boats now lasting for decades with that material gone. And now today you'll find there's many, many material choices that the builder has that can give the boat unique functionality depending on the purpose of the boat. So what's different about composites versus metals? Well, with metals, you specify the material. There's all different types of material specifications for various grades of steel, aluminum, alloys. We bring those together into the shipyard, for example, if we're building a boat, and then we simply form, shape, weld, and bring those materials together. So in a large part, the materials are already formed or made when we get them. Well, with composites, we're really a step backwards from that. So we're going to take the raw materials that are used to make composites and we're going to create the material. In essence, the material is created when we laminate the part. So we're going to combine fibers, resins, coatings, core materials, all these things we're going to talk about in this class, and combine them onto the product itself, and how well we do that really determines the material properties. As opposed to metals, we know those material properties when they get here. So for us, we focus on our raw material properties quite a bit. So we need to have good raw materials, and then we need to have skilled workers who know how to use those materials correctly so that we get the product that we want. So some of the factors that influence strength. And if you're in the job of laminating, this is an important part of the job. First is the resin to glass ratio. So there's a certain amount of fibers that we want and a certain amount of resin. And each material has its own unique resin to glass ratio. It's dependent on the fiber architecture and the material process that we're using. Getting the right resin ratio is important. If we don't have enough fibers in there, we have too much resin, we'll have a brittle part, it'll be heavy and potentially break. If we don't have enough resin in there, we're not going to be able to connect the load paths from the fibers together, and we could have structural failure, or in the case of a boat, it could leak. Now, when we do composites, we will follow something called the lamination sequence. And so these materials will come in plies, and these plies will have to get stacked in a certain order. It's very important that the worker understand the stacking sequence called the lamination schedule. We need to follow that lamination schedule and put the laminates in the order that the product was designed for, whether it was a boat, a truck, or a trailer. Next, it's not good enough that we just get the fibers in the right stacking sequence. We have to point the fibers in the correct direction. So fiber orientation is very important. So for each of these laminate materials, they're supposed to be laid into the part in a certain direction. If we miss that direction, guess what? We're not going to get the same properties that we expect. And so it's important that we have the proper fiber orientation. So now with all that, we've added the resin, the stacking sequence. We pointed the fibers the right way. Now we need to work those fibers. We have to ensure that the resin gets deep into those fiber bundles. We have to get the resin into all the fibers, saturate them to the proper level. If we have too much resin in some areas, we've got to move that to other areas. If we have too little resin in other areas, we've got to add resin. So we've got to distribute the resin, consolidate the laminate, get all the voids out, and allow the resin to cure. So it's important that we get a uniform fiber wet out and consolidation. This is what gives laminates and composites its great properties. If we follow all these basic steps, we'll have a laminate with the properties we desire. So as we look at different structures, there are different types of loads, and understanding the loads are somewhat important as we work with the materials. So marine structures like boats, in particular small boats, their worst loads are bending loads. These loads come from hitting waves. Also, they can be like on the boat trailer. When you put your boat on a spot on the trailer or on a bunk, that can be a high stress riser. As boats get bigger and bigger, that local bending load becomes less. And as boats get up to 200, 300 feet, now the major stresses are more important, and the boat behaves like a giant beam. Aerostructures tend to not work with a lot of bending loads like we do see with boats. So they're going to have more in-plane loads on their structures. Well, that was the very first slide set, and we'll have a whole bunch of series that are going to take you deeper and deeper into composites. But this gives you the very first introduction. I look forward to talking to you more on these other classes.